Hey everybody. Today, you can see on the title there, we're going to talk about something called Sine Law. And so where we're coming in on today is we've got some practice working through our right angle trig, some SOHCAHTOA, and we're pretty comfortable using our trig ratios. And what we're going to do is we're going to extend that today into something called Sine Law. So in order to do that, I want you guys to just work through the two very, very quick problems you see on the screen. This is some introduction for us and some reminders for us with regards to some algebra. So go ahead, take a moment, work your way through, pause the video now. Okay, we're back. These two problems I really just want to walk through with regards to if you have to solve your equation and you notice you have your variable on the top, it's a nice, easy multiply out your 5 to now end up getting your 47ths. Now, the instruction says to go through and find an approximate value. Normally, you would just give that exact value. Today, I want you to just go through the process of generating that approximate, and you would get approximately 5.71, something like that. You take a look on B, and you notice your variable is on the denominator. So that causes a little bit more of a problem. In order to isolate that denominator, you need to multiply everything out. So we might as well at the same time multiply out the 8. And so we can end up getting our 40 equals 7x. And that is that action that you tend to think about when you say, hey, well, I'm going to just cross multiply when I have my fraction equal to my fraction. And now that you have your variable off the denominator, you're now able to go ahead and to get rid of your times by 7, you divide by 7, and we come in on our approximate, again, notice 5.71. You'll notice that I've named that as an approximate by showing my rounded symbol. That is my equal sign with the dot on top. And there we go. Okay, hopefully that was pretty comfortable. You should be asking, why am I even doing this? That's really going to be the mechanics that we do for a lot of today. Okay, now that we have that, I want to change gears. So, what you see on the screen now is an instruction that you should be very familiar with. The idea to solve that triangle. So, you are going to have to take a look, triangle ABC, find everything that is missing on triangle ABC. You start to take a look and you go, hey, well, I've been given angle B, I've got 105, I've been given side B, my 23 centimeters. I've also been given side C, my 18 centimeters. So I've got both my angle B and side B, and then I got my side C. That would mean that you would have to find all of the green. Angle A, angle C, and side A. Okay. You are taking a look at that and hopefully noticing we've got a problem. You take a look at triangle ABC on the screen and you notice it's not a right triangle. And because it's not a right triangle, you're limited in what you can do. Now, if I was to go through and just change up my diagram, like if both side C and side A were marked as equal length, well, then you would know that side A was 18 centimeters. Since that's an isosceles triangle, well, then you would know that angle A and angle C are equal. And therefore, you could find either one of them by taking 180 minus the 105, seeing what angle's left over, and then dividing it by 2. But because that orange is not true, all of the consequences of it, I cannot assume. Okay, our problem is we're able to use trig, but only on right triangles. Well, can we start to examine trigonometry on non-right triangles? And that's where we're going to go today. So the first thing that I want us to notice by taking a look at that triangle, we have a major problem with our skills to date. We are only able to use Pythagorean theorem and trig on right triangles. Well, maybe we can extend that. Okay, let's examine something else then. You take a look at what you've got on the screen right now. What we're going to do is we're going to go through a proof for how we can examine the relationship between non-right triangles, their angles, and their sides. You'll notice that what I have on the screen is a triangle, and I would like you to copy down that triangle. Now, what I also want to just highlight for you, can you please make sure that the triangle you draw on the screen does not look like an isosceles triangle? We just discussed that on the previous problem, that had it been an isosceles triangle, you could have figured out some other things. I want to make sure that for our proof, we don't draw what appears to be an isosceles triangle so that we don't make really bad decisions. Okay, we want to make sure that it's obvious to us. So when you take a look at the triangle I've drawn, I'm going to have like a flatter side and a steeper side. Like, make sure that the slope between those two sides is noticeably different. Make sure it doesn't look like a right angle, because then we would just use our SOHCAHTOA. Okay, we're going to walk through a proof for something that is going to allow us to deal with manipulating a non-right triangle. Okay, first off, so we can talk about the triangle you see on your screen, let's label it. So I'm going to call it triangle ABC, just like the previous triangle. And here becomes our starting point. Really, it backs up to, what skills do you have at your disposal? I hope for a lot of us, we recognize that the fact that it is a non-right triangle limits us. And had it been a right triangle, then we would be able to do other things. So my argument to you then is, turn it in to what you have the most skills for. Now, you're going to look at that and go like, I can just make it a right triangle? And I'm going to tell you, no, you can't just make it a right triangle. But if we drop a height in, just as you see on the screen, and I can denote that as a height by saying, there's my perpendicular marker, my 90-degree marker, then what I've just done is I've just changed triangle ABC into two right triangles coming together. Now, I'm going to, just for the sake of argument right now, call where that hits point D. That is absolutely not necessary. But it just helps me to kind of say then that triangle ABC is really triangle ABD added together with triangle DBC. Okay, why did I do it? So that now I have right triangles. Now I have more things at my disposal. Okay, so like, what am I even going to do about it? Well, can we make sure that we label our sides? I don't want us to be confused at all. The sides of our original triangle would be side A, side C, and side B that goes all the way across the bottom. Those are still my sides. But because I just dropped in that height, I could now say that I also have this side, let's just call it H for height. Okay. I'm going to work my way through everything I know or everything that I have at my disposal, at least as much as I can that's easy. Well, can we zero in on the left side triangle? You don't need to write this down, but what I'm going to do is I'm going to zero in on triangle ABD. And I just want to see all the things that I have at my disposal. That is a right triangle. So I could have Pythagorean theorem and relate Pythagorean theorem on that triangle. My problem becomes, I do not know the length of AD. This is why I wanted to make sure that it did not look like triangle ABC was an isosceles triangle when you drew it. I'm going to draw something on your diagram. Please do not. When we work our way through that one, I do want you to notice, if triangle ABC was an isosceles triangle, then when I drop that height in, I would have broken up my bottom side into 2 equal parts. By definition, if I have an isosceles triangle and I drop in a height, it cuts the bottom dimension exactly in half. Well, I'm hoping that by you drawing that triangle with different slopes on its sides, you can clearly see that AD does not equal DC. So, if I come back to, I don't know what AD is. So on triangle ABD, Pythagorean theorem isn't that useful. Okay, well, what else could I use? Well, I don't know what angle B is anymore. You'll notice I took the old angle B of our original triangle and I broke it up by dropping a height in there. That means I don't know what angle B is. Not really useful. But you may also notice, though, I do have angle A in its entirety. I have not affected angle A at all. It's still the original angle A. And so what can I do from that angle A? Well, if I take a look in that triangle, I notice I do have the opposite side, and I do know my hypotenuse. That means opposite and hypotenuse, I can build a sine ratio. So I could build the equation that the sine of A has to equal h over c. Now that's really the only thing I can do within that triangle. Because I don't know the length of AD, I can't use Pythagorean theorem. Because of that, I don't know my cos ratio because I don't know my adjacent side. And I won't be able to figure out my tan ratio because I don't know my adjacent side either. The only thing I could come up with was my sine equation, my sine ratio. Okay, I'm going to leave it there with that left triangle because that's the only thing I can really come up with. But what maybe I can see is I could jump over to the other triangle. And if I looked inside triangle DBC, I could do the same thing. I still don't know my bottom side, but I do have all of angle C. From angle C, I have my opposite and my hypotenuse. I could build another sine equation. Opposite over hypotenuse. Now, okay, I got to that point, and then I kind of stopped. Because I'm not sure where to go. I don't have any numbers for anything, so it's not like I can calculate stuff. But maybe if I was to say that that was equation 1 and that was equation 2, you might be able to see something. Okay, if we can't see where we're going to go, at the very least, could we simplify both of those equations? And really simplify is maybe not the best word. Could we manipulate both of them? You notice you do have fractions in there. Like, what if I took a look at equation 1 and said I didn't really like my divide by c? Well, then I could choose to multiply out that c. And I could manipulate that equation to say that h equals c sine A. Okay, why am I doing that? Well, if you notice, that h is the only part of that equation that was not part of my original triangle. Remember, we dropped in the height. We did that. That's not part of triangle ABC. So maybe what I want to do is I want to get that h all by itself. Well, if I get that h all by itself in one equation, then maybe let's get the h all by itself in the other equation. To get rid of my divide by a, I could times by a. Okay, why is that useful? Well, if we think back to Unit 2, you notice you have a system of equations. And within that system, you have the same variable, h. Well, what I could do now is I could sub equation 1 into equation 2. That is, h equals c sine A. Well, let's sub it into equation 2 wherever I see my h. That's going to give me C sine A equals A sine C. Okay, that is super useful. We just don't know why yet. But if you notice, every part of that equation is a part of my original triangle. It's all C's and A's. Okay, how can I manipulate that? Well, I can manipulate that a bunch of ways. I'm going to guide you a little bit on this one. You will notice that you have a side C, but you also have an angle C. You'll notice you have an angle A and then a side A. What if you just said, I want to get all my stuff that's the same, that corresponds with each other, on the same side of the equal sign? So maybe what I want to do is I want to get that A, side A, over with angle A. Well, if I'm going to do that, then I might as well get my side C over with my angle C. You'll notice that they're both attached by multiplication. So, to get rid of, and I'm going to do this in its parts, to get rid of that times by A, I'm going to divide it. But now I can get rid of my times by C, and I'm going to divide it. And what you just came up with was something that's called Sine Law. Okay, I know it has no meaning to you right now, like absolutely none. But what I want to do is I want to kind of sum up what we've done on the page. This is extremely important. If you go back to your original triangle, you will notice that what I am boxing in purple is a relationship between angles and corresponding sides. It only contains the information on my original triangle. So I know the way that angles A relate to corresponding sides A with my sine ratio. Okay, before we go through and we write down like a formal statement on what sine law is, can we just go back to our triangle for a second? And I want you to take a peek at it and just notice we could have done something different. Okay, what am I talking about? Are you guys good that I dropped in a height from B, but that wasn't the only way that I had to make a right triangle? I could have dropped in a height from A and made right triangles. Or I could have dropped in a height from C. Let's just look at me dropping in a height from A. By dropping in a height from A, do you notice that now I have the full angle B and the full angle C? I'm hoping you can picture doing all of that red algebra on the right side. But instead of having angles A and angle C, I would have had angles B and angle C. And so instead, I would have built what I boxed in purple, a relationship between B's and C's. Okay, to save all the time of us doing that then, really what that means is I can extend my sine law. I'm going to erase part of that box, and really what I'm going to do is I'm just going to extend it. On the other side of that, I could have now said, well, then that has to be equal to sine B over B. And there is my sine law. Now, you take a peek at that sine law, and it's going to have no meaning to you right now. If I go to ask you, hey, memorize sine law, then sometimes a mistake you can make is to go, oh, so that's sine A over A equals sine B over B equals sine... And I'm like, no. That's a formula that has no meaning. What does sine law actually say? Well, it says that there's a relationship in my triangle. Okay, I'm going to go back and I'm going to erase all the heights and everything that was not a part of the original triangle. When I go and erase all of that stuff and now draw in my triangle again, I would have side, side, and side. I'm also now going to be able to just label that bottom side as side B. What my sine law actually says is it is a relationship between an angle and its corresponding side. That if I take the sine ratio of angle B and I compare it to side B, that's what that ratio says. Take the sine of the angle and divide it by the side. Compare it. Then if I make that comparison, it has to be exactly the same as if I do that with any angle and its corresponding side. So what does sine law really mean? I'm going to ask you to get it down in words. It really means that the sine of any angle inside your triangle compared, and I'm going to put the word ratio, because that's what we talk about when we say we're going to compare something by dividing. Like how many times bigger is something? The sine of any angle, its ratio, compared to the corresponding side. So I'm talking about taking angle B and comparing it with side B, angle A with side A. I'm not talking about taking angle C and comparing it with side B. No, with its corresponding side. Then the sine of any angle compared to the corresponding side is the same throughout the triangle. That anytime I compare my sine of my angle with its corresponding side, that ratio is the same throughout the triangle. That is a super important feature for us. That property allows us now to work with non-right triangles. Okay, what I want to do now is I want to hop back and I want to start using sine law so we can see how it is a functional tool for us. Okay, let's hop back to problem A, the one that was stumping us before. So there is our triangle, ABC. We notice it's a non-right triangle, and then we've got our information listed. Okay, I'm going to do something right now that I would never do if this was a problem we were going through to solve. But what I want to do is I want to show you how sine law is functional, but we're going to stumble with it a little bit. So if I take a look at that triangle and I just wrote out a generic sine law, sine A compared to its side A has to equal the sine of B compared to its sine B, which has to equal the sine of C compared to its side. There is my sine law. The sine of any angle compared to its corresponding side is the same throughout the triangle. If I just took the information that I had on my triangle and I started to plug it in, I'm going to notice that I start to have some known things. Well, I do not know angle A, and I do not know side A. I do know angle B. I do know side B. I do not know angle C. I do know side C. And if I plugged all that information in, so now I have my purple equation of 3 fractions equal, you'll notice that I've got some things that are known and some things that are not. If I was just to say, this first fraction is not very useful to me at all, because I don't know what angle A is nor side A. I know neither of those corresponding properties. Not useful. Can we jump down to the last fraction? Well, that fraction is at least somewhat useful. Like, I've got side C, I just don't know what angle C is. The one that is very useful are my B's. If you look at that fraction, I know the top and I know the bottom. Those are all constants. I can calculate that stuff. I tend to refer to that as that's your magic ratio. That one is your magic ratio within this triangle. Can I get you to take a look back on my triangle and notice there was angle B, there was side B. I know a pair of corresponding sides and angles. I know one of them, my B's. So my B's become really important to me. If I just left the crossed out fraction all by itself, then what I have is a number on top. It's an ugly number. The sine of 105 is a big ugly decimal comes up on your screen, but it's a number. Over 23 has to equal the sine of C. That's a variable. I don't know what that is. Over 18. That purple equation, I can solve. I'm just going to circle it in red. That's my only variable. And if I have one variable in an equation like that, I have the means to solve it. Now, what I'm going to do is I'm going to pause there for a second, and I want to hop back to something that we previously looked at. Take a look back at question 1a. You will notice that question 1a is the same thing that we were just working through. The only difference is my variable is not on the left, it's on the right. So instead, I would have had 8 over 7 equals x over 5. I have 3 parts of the 4 parts within that purple equation known. I have my magic fraction where I know both parts. Now, to get the x all by itself, I just have to multiply out my 5. That equation is what we're going to solve. It just looks uglier. So let's jump back to us using Sine Law. So if you take a look at my purple equation, you notice my angle C is the only unknown. So if I needed to multiply or to solve for that, then I need to get rid of this divide by 18. I'm going to multiply it out. So my sine C would then be isolated. I would have my 18 times my sine 105. You notice I don't write my multiplication in there. I know if I don't see an operation, it means times. That's divided by 23. And there you go. You have the ability to solve that equation. Okay, let's finish it off. You do not have to, in terms of formatting, ever show me this line. But it might be something that you like to put in to remind you how we're going to tackle finding angles. If you recall, for me to find my angle, I need to go backwards, which means I need the inverse sine of that big, ugly amount. That is really messy on top. Let me clean that up. I gotta clean up the whole thing. So I need the inverse sine of 18 sine 105 over 23. Now we need to figure out our button pushing process. So you need to go through and figure out what the value of sine 18 sine 105 divided by 23 is, and then take the inverse sine of that amount. You will have figured out your keying sequence if you can get down to an angle of approximately 49 degrees. Hopefully, you're able to figure out the keying sequence that gets you there, and we match up. Okay, I want you to take a look at what we've done in purple, because what we've done in purple is what you would be responsible for showing me. I'm just going to put some stars beside some things. That line there with the star is your application of Sine Law. That's you using Sine Law. I need to see it. The next line in purple is you giving me the exact value for sine C. There's been no rounding there. I need to see that. But you can skip over that orange line. Like, we know how to, if given the value of a sine of an angle, to find the angle by taking the inverse. You don't have to show me the orange. And then obviously I need to see you finding your angle and our rounding rule for angles. If we don't see a rounding rule, we round to the nearest degree. You give me those 3 purple lines and you have a great solution using sine law. Nice. Okay, the instruction has been to solve for that triangle. I'm going to help us out a little bit by just labeling what we just found on our triangle. We just found that angle C is 49 degrees. And that's a little bit sloppy. I want to clean that up too. There we go. Okay, we got to still finish off solving the triangle. You'll notice we're missing both of our A's now. Except I think we cured a major problem. You know 2 of the angles inside the triangle, which means you know your third. So I'm going to sneak up onto the left underneath that diagram because everybody should now be able to tell me that A is going to equal 180 minus the sum of the other 2 angles. We know all 3 angles add up to 180. So if I take 180 minus the other 2, well, 180 minus the other 2 is minus 154 degrees. And that's going to tell me that angle A has to be 26 degrees. Nice. And there we go. Okay, well, we're still missing side A. But maybe you can see how we can find it. That is, when you take a look at that diagram, well, it's still a non-right triangle, so I can't use Pythagorean or my SOHCAHTOA. But I do know angle A. If we can look back up into the line I'm boxing in green, all I'm going to do is I'm going to get rid of that first fraction on the left side, everything I circled and had crossed out. And I'm going to rewrite in the fact that that was sine A over A. We didn't know either part of that. It became useless for us within sine law. But now you'll notice we know what angle A is. It's 26 degrees. I now know one of the parts of that fraction, which means I can use it with my magic fraction, my magic ratio, and I could use sine law again. Okay, what is that going to look like? So what I want to do is I want to go through and deal with sine law. I'm going to ask you to not write this down. I'm going to actually write something where I wouldn't recommend you doing this way. I just want you to see it written down. So what I'm going to do is I need to find or use that fraction of sine 26 over A along with my magic ratio, the one where I know both my B's. Okay, I want to highlight for us. Look where your variable is. It's on the bottom. And maybe you recall, it took a little extra work for us if it was on the bottom. Okay, all I'm going to do is I'm going to pop back to the top of our page one more time. So let's take a look at B now. You'll notice B is an example of where we have our variable on the bottom. There it is. I'll circle it in purple now this time. There's my X. So for us to go through and solve that equation, it required a little extra manipulation because we had to multiply to get our variable off the bottom. Adds a little complexity. Biggest part I wanted to show you with both question A and B. Does it matter how you set it up? The argument is going to be it only matters for the work we have to do. It does not matter for the answer we get. Like our solution, it doesn't matter whether we choose to set things up with the variable on top, like in A, or on the bottom in B. So my argument to you would be, if it doesn't matter how we set it up, in order to get the correct solution, it just matters in terms of the work we do, then why not pick the way that's going to be easiest for us to solve? That being our method in A. We like having the variable on the top. That way we never have to worry about multiplying it out. So I want to hop back into our sine law, our solving triangle problem. So if we take a look back at that problem, you'll notice in red, because I've used my sine law just as the way I've given it to you, that's forced my variable to be on the bottom, which shouldn't be a problem. We just have to multiply it out, but it does mean that we've got some extra work to do. You'd have to multiply out your A to then get an A sine 105 on that side. But then to get the A all by itself, you now have to re-divide out. And I'm going to argue to you why. I'm going to go back and I'm going to erase that entire version of sine law. The one where you see the variable on the bottom. And instead, I'm going to use a different version of sine law. I'm going to flip it. I'm going to go and put my variable on top. Well, if I understand sine law then I need to compare a side with the sine of its angle. And the way I compare those is the same throughout the triangle. So if I put my side on top, then I have to be consistent to always put my sides on top. I think what you see in red there is the best form of sine law to find a side. You'll notice now for me to solve for A, all I have to do is multiply out my sine 26. So my A is going to be exactly 23 sine 26 all divided by sine 105. Whew. That's ugly. But that's the exact value for A. Exactly that. Now, we just don't talk about it that way. So now we got to push some buttons, and you figure out your keying sequence to be able to go through and get approximately 10.44 centimeters. Okay, you figure out your keying sequence. If we need some work on that, then just pause the video. What I want to hit up right now is a key component for us using sine law. Can you look back at what I boxed in green and how that led my purple? If I'm solving for an angle, then I put angles on top. But now, can you jump over to my red solution? If I'm trying to solve for a side, then I put sides on top. All that does is it makes my algebra afterwards easier. Okay, I'm going to do the same thing. I need to see your application of sine law. I need to see the exact value for your side. And then I need to see a rounded figure because that's the way we talk about it. There you guys go. You have actually probably solved your first non-right triangle. Well done. Okay, I want to now jump into B because we're a little bit better with this stuff than we were through A. So let's take a look at the diagram with B. What I'm going to do now is I'm going to assume, rightly or wrongly, that we're good with sine law. And obviously we're not, like not after one problem. But I want to talk about it with a different tone. That is a tone where we do have a better understanding. So let's take a look at the triangle given, triangle LMN. Now, if I have sine law in my background, and I notice that I'm working with a non-right triangle, then my first instinct is I would like to use sine law. My problem is, in order to use sine law, I need a side and its corresponding angle. And I notice that when labeled, I do not have both of any one of those L, M, or N. Like if I get rid of all those marks that I just put on the triangle, you'll notice you have angle L, but you don't have side L. You have angle N, but you don't have side N. You have side M, but you don't have angle M. And so on first look, it goes, hey, we don't have sine law. But that's what we need to be able to use sine law, a corresponding side and angle. I'm hoping that even within that discussion I've just had, that I would have a lot of you that would go, but wait a second. I do have the ability to find M. It might not be labeled on the triangle, but I know what it is because you gave me the other two angles, and that would be great. So what we can do then is we can go ahead and we can find angle M first. So to find angle M, that is 180 minus the sum of the other two angles. That is a 51 and a 63. Now what I've put in orange, you would never have to show me. But in all seriousness, I would strongly recommend putting down that orange. It really doesn't cost you a whole lot of time to go through and write that down. Now we have our 114. What you would have to show me is you listing all the properties that are missing. So just like when we solved right triangles, when we solved non-right triangles, you have to list out the missing properties. If you gave me the purple, you're good. Again, I strongly recommend writing down the orange. It doesn't cost you much, but it helps to organize everything. Okay, now that I know that angle M is 66, I could choose to label it on my diagram. And if I do, now you can really see you have a corresponding side and angle. There's your magic ratio. There's the ratio we needed. Okay, I'm just going to get rid of that big blue outline because now we have to decide, what are we going to find? Are we going to find side N? Are we going to find side L? Okay, my advice to you, find the shortest thing first. I always find the shortest thing first, the smallest side length first, the smallest angle first. We'll talk about why as our unit goes on, but my recommendation, find smallest first. So in that case, I have an angle L that has a 51 degree angle, and I have an angle N that is a 63 degree angle. Well, big angles make big opposite sides, and small angles make small opposite sides. That's telling me I'm going to find L first. So I'm going to go through. Now I'm looking for a side L, so I want to put my side on top. So that's what I'm going to do within my sine law. Again, everything that I do not see, I'm going to put in orange. Well, my sine law then would be L over sine L equals, and now I want to use my magic ratio, the ratio where I know both, that's my M's. I do not need to see you writing down your blind formula for sine law. I don't need to see it. That's going to become background knowledge for us. Let's just use it. I do need to see your application of sine law. So L over sine 51 degrees has to equal M, which we know is 20, over sine 66. I have to see that line. That is your application of sine law. Now, I need to see your isolation, your exact value for side L. So, to get rid of a divide by sine 51, I'm going to multiply by sine 51. Now, how do we talk about that side length? Well, we're going to round it. And our rounding rules, if we don't know, or if we aren't given any rounding rules, round to 2 decimal places. And when we punch that in, we should end up getting an approximate, you see my approximate symbol, of 17.01 meters. Nice. Okay, I think we do have a moment to try some stuff on our own. So you can take a peek and you notice that we now need to find side N. I'd like to give you a moment to try to see, get some feedback. Are you comfortable using sine law? So let's try it on our own. Let's pause the video now. Okay, we're back. So same thing, if you chose to write down your formula for sine law, I don't think that's a bad thing right now because it's helping to drill it in. But again, I do not need to see it. That's why it's in orange. You got to give me the purple, though. N over sine 63 is going to match with 20 over sine 66. Okay, hopefully that was your first or second line, but it needs to be there. Now we can get rid of our divide by sine 63. So we're going to multiply it out. At no point do you notice I am ever calculating and rounding any of this off throughout my solution. The only time I'm going to calculate and round anything is when I'm turning my exact final value into my approximate for how we talk. And if you got down to approximately 19.51 meters, then well done. I think that's telling you you're starting to get pretty comfortable with sine law. So take a peek at that full solution. We have solved for everything that was missing. If we matched up with that, then I think that's given us some good feedback. Okay, I want to tackle one more problem before we go. So if you take a look on the screen right now, you'll notice that I've given you a problem without the diagram. And so what you see then in problem 3 is a list of properties. It tells me that we're working with triangle ABC. And it tells me that angle A is 35 degrees, side A 15 centimeters, side B 12 centimeters, and has asked us to solve that triangle. Okay, I think we should absolutely be drawing a diagram. So, one of the things that I want to impress on you, when we go to construct triangles, you really want to make sure that you build a relatively proportional triangle. Some of us make a mistake of we just end up drawing the same triangle over and over again. Like they tend to look like an equilateral or an isosceles. And then we just label it differently. Like we might sit there and say, oh, well then this is a 35-degree angle, but so is this a 35-degree angle, or so is this a 35-degree, and they're all very different angles. So this does not really impact you in our course. In grade 10, it doesn't. In grade 11, it will have a significant impact on you. So my advice, go ahead and build your triangle angles out. So what I'm going to do is I'm going to build a 35-degree angle. Now, I'm not actually going to pull out a protractor. No, we're not. We're talking about estimating. It's a sketch. But what it means is if I was to put on the bottom side of an angle, there's my bottom ray, and then I was going to estimate 35 degrees. What I do is, in my mind, I tend to think, what is like the perfect diagonal of a square? Like if I was going to think about a square's diagonal, then I know that creates a 45-degree angle in the corner. And all I do is I estimate based on that 45. So, since 35 is a little bit less than that, then all I care about is drawing something that visually looks smaller than the diagonal of a square. That's all. If my angle had been 65 degrees, then I would draw something that looks bigger than the diagonal of a square. That's all. But that quick little estimate is really going to help me out. So if I got rid of my orange then there is my 35-degree angle. I'm going to label it angle A and 35 degrees. Okay, what that's telling me then is I've been given side A, and I'm hoping that we're good, that side A is neither ray of that angle of 35. Like side A has to be opposite over here somewhere. Side A has to be opposite angle A. So what each of these rays are that we don't know how far they extend, those have to be side B and side C. So I'm going to hold off trying to draw on angle A right now, and I'm going to decide to make one of those side B. So maybe for me, I'm going to make that visual on the top. I just tend to extend the top. That's my own personal preference. But if I did, that's me now saying that this top ray has a length of 12. Whatever I want to think 12 is, that's my B. Okay, well now what I could do is I could drop in a side that I thought was like a little bit longer than that. And if I just tried to estimate, like what I thought was like a little bit longer, then maybe I get something like that. And I need to extend that all the way down to the bottom of angle A. Now what I can do is I can enclose my angle. Remember, that bottom side of angle A is a ray. It goes on forever. I can now enclose it to construct my triangle. I know that my red side was my side that was A, and it was 15 centimeters. Since my blue side was side B, that makes this angle angle B. Since my triangle is called triangle ABC, then this now becomes side C, or angle C. And that's how we can go through and construct our triangles. Okay, now that you have that diagram, I think you should be good to be able to solve. So I think this gives us a really good opportunity to try our sine law on our own. Okay, I want you to try it on your own. Pause the video now. Okay, we're back. So I am hoping that you can see within the problem, you were given both of your A's. So you were given, with the given information, given our magic ratio. You were also given side B, which means I can find angle B using sine law. Same color coding as before. I do not need to see the orange, but if I'm looking for angle B, then I want to put my angles on top. Since I'm using my magic ratio, that would also incorporate my A's. Okay, first line I would need to see. You are finding the sine of B compared to side 12, and that has to compare the same way as the sine of 35 degrees with side 15. Okay, we should be good then to get rid of that divide by 12 by multiplying it out. As I mentioned earlier, if you like to put in that inverse line, then feel free. I never have to see it. And I just put an angle measurement on my side length. Wow. Let's correct that. Okay, you can go ahead and you can push some buttons now. And as we push buttons, we're finding an angle, so we're going to round to the nearest degree. And as we work our way through, we should be rounding off to approximately 27 degrees. And make sure we've got that approximate symbol on our angle. And there we go. Okay, now that we know what angle B is, I want to give you a moment that if you hit a snag coming up with how to begin that problem, we got a chance to try to finish it off now. So you go ahead, work your way through, try to finish it off. Pause the video now. Okay, we're back. I'm going to shrink that down just a little bit so that we can keep working through solving. If I have angle B being 27, I now have two angles within my triangle. That tells me I really have three. I can find angle C by taking 180 minus the sum of the other two. And again, that does not cost you much time at all. Before I put that equal sign in orange, I do need you to be able to state that C is going to be 118 degrees. Okay, now that we know what angle C is, you now have one of those angles where you do not know the opposite side, but we should be good to find angle C using sine law. Okay, I'm not going to write down my orange version this time. I think we could be a little bit better with that one. So I'm looking for side, so I'm going to put my side on top over the sine of 118 That has to equal, and I'm going to use my magic ratio again. Those are my A's. My side on top, the sine of my angle on the bottom. I can now get rid of my divide by sine 118. Yikes. And I am putting in way too many ones. And that is divided by my sine 35. And now when I go ahead and push some buttons, I am finding a side length. There is no default rounding rule, so I'm going to round to 2 decimal places. And when I do, I'm going to get 23.09 centimeters. And there we go. Okay, especially in a problem like this one, where you are not given a diagram, well then I think it is valuable for you to take one moment and just try to make sure that our proportionality matches up. So take one moment, and all I'm going to do is I'm going to label everything on the diagram. That side C is now that angle B is that. So if you recall, our proportionality says small angles create small opposite sides and big angles create big opposite sides. So let's do our quick check. Does the smallest angle give us the smallest opposite side? Does the largest angle give us the largest opposite side? And if that matches up, then chances are we should feel pretty confident with our triangle. Okay, your job. Jump in, get some practice, and make using sine law as automatic as possible. Okay, good luck.